is a professor of animal science at Iowa State and Lush Chair of Animal Breeding and Genetics. His research is focused with the development, adaptation, and application of numerical methods for the integration of genomics and phenomics data. More specifically, Juan's main interest in applying such methods to understand the genetic basis of animal behavior and how that impacts the production and welfare of livestock and poultry raised under group housed conditions. Thank you.
Okay, thank you very much. Thank you for the introduction, and thanks to the Iowa Pork Industry Center for having me here to present, and thank you for staying in this presentation. So today I will talk about some of the work that we are doing in this area of sensing for phenotyping, for measuring traits in animals and their environment, and that how can we use that for breeding and for management purposes. So, as it was mentioned in the introduction, one of my focus is on understanding behavior and how that how can we manage or breed for certain behaviors that lead to animals that do better in groups, not just individually, but also as group members. And that has ample application for many production systems, but I work mostly, I would say 90% plus of my effort is dedicated to pigs. So there are production systems that have traditionally been based on grouping, housing animals in groups. For instance, win to finish operation is a group endeavor, usually group housing endeavor, and in those cases that's done because it's easier to manage that way. Try to manage as homogeneous of a group as possible. It's economically convenient, and the phenotypes that are measured, the traits that we measure on these animals are measured exactly in the production condition that we are expecting them to be performing. This allows for social interactions, etc. So whatever happens behaviorally there is somewhat integrated, and the effect of that is manifested in the traits that we are measuring. In other segments of our industry, that it's the case of gestation, it's been, I want to use the word historically, but you saw it today in the presentation that around the 70s, we went to to individual housing. So historically, in the recent history, individual gestation is the most common way of managing sows and gilts. And in those, why we do that? Because it was proven over 50 years ago that was economically more convenient, and it's easier to manage an individual sow that way. And of course, the phenotypes have been measured under those conditions for forever, and for at least for 50 years. And it's been genetic progress and management recommendations done considering this system. And in this system doesn't allow for the expression of social interactions, but it wasn't relevant at the point. And then, due to several factors, but probably the main one is societal pressures and legislative and commercial mandates due to societal pressures, we find our industry going from this to this in these segments of our production system. And so now we put the sows, for instance, or the gilts that were raised, were selected, bred under these conditions, we put them, or their progeny, to produce under these conditions. And first question is how we manage these animals individually, if they need individual attention and they are in a group. And then the other one is that how we measure stuff in them to keep our breeding schemes and management system going. And also now that there are interactions that become more obvious, and the interactions that become more obvious probably and the negative interactions between animals, such as aggression and things like that. So I've been working on this for a while and thinking about these problems for a while. I will show you a little bit of work in this area. So why I am particularly interested in breeding, in behavior in the context of breeding and management, it's for two reasons. One, the main one, of course, is to select animals that do better in groups. As a breeder, I want to remind everyone that the breeding solution is forever. So you bred animals in a certain way and you don't have to worry about it. If you manage animals in the way, you have to repeat that management over and over. It's not a bad thing, but demands continuous effort, while breeding is more of an investment. You invest and then you kind of, quote unquote, solve the problem in the long term. But also to manage, to observe behavior and draw management decisions. So I will be talking about this. So from the breeding perspective, we are interested in the effect of genetics or genomics on performance traits, but also we might be interested in the effect on behavioral traits. Animals that are more aggressive or less aggressive or whatever, or more cooperative, etc. But also the behavior of an animal affects the performance of everyone else who's in the group. If you have an animal that is very dominant and competes a lot for feed against their group mates, that animal will affect, let's say, the feed intake and the growth and the feed conversion ratio of everyone else. And because that behavior of this animal has a genetic basis, then the genetics of this animal affects the performance of these other animals. And that's something called this indirect link through this path. And that is called a social genetic effect that I will talk about next. And also, the way that animals behave as a group or individually might be used as an indicator of welfare or other situation, or for instance, health, and then that might trigger some management decisions. So one thing that I have to admit, obsessed with is how to measure behavior. Because one thing is to make anecdotal observations of how animals behave, and everyone has done that. If you manage a herd and you have a very specific animal with a very particular behavior, but we need to look at the behavior of every animal on a continuous basis. So I will be talking about some of these things. So one way to measure behavior is to use some type of sensor, and then that sensor interacting with a computer program or with a human or with both of them. And so I will take some time to talk about different type of sensors. There's sensors that are considered remote sensors. And so these are sensors that are away from the animal. It could be a camera, it could be a microphone, something like that. And they capture signals from the animal itself or from the environment. And then there has to be a way to link that signal to the individual animal. And so in those remote sensors, as you will see, the challenge is to link the signal that the camera, for instance, is recording to who's that one that is doing that. There's other sensors that are called wearable sensors. These are on the animal. And these sensors that are on the animal are easier to know who's producing the signal that comes from the sensor, because each sensor produces an individual signal. So let's say it's an RFID tag. When the animal approaches an antenna, you know that that animal is at that place doing that. If the antenna is inside of feed trough, well, the animal is the one that is eating. You assume that it's eating because the head is inside the trough. So in that case, these wearable sensors, another case are, for instance, accelerometers or activity monitors in general that are also placed on the animal. These sensors produce a signal that is very individualized, very easy to associate with each animal, but it usually is a signal that has a very low resolution in the terms of the type of data that I will give you. It will tell you this animal is here, or this animal is moving up and down, things like that, very simple things, not as much as a richness of data as, for instance, a camera. But you solve that problem. And then we have proximal sensors, which are sensors that usually work in combination with other type of sensors. And these are in a place where the animal comes to and they measure something. For instance, there might be in an automatic feeding recording system for growing pigs, commonly used in the breeding in nucleus farm for breeding pigs for more feed efficiency. There is a load cell in here and there is an antenna. So the antenna works with this RFID to identify which animal is in there, but there's a load cell that will tell us how much feed disappeared while the head was stuck in the feed trough. So this proximal sensor, which is the antenna, the load cell, working together with the antenna will give us feed intake, water intake in other species or even in pigs, etc. So this combination of sensors is very common. Of course, you can combine a camera with an RFID and see what, once you identify an animal in a certain location, try with the camera, figure out what it's doing. So there's now applications that are emerging in that area. So the first, and I will walk you through 3 projects that we are working on in my lab right now with my students and postdocs, and in different stages of completion. And the first one is, what can we do with sensors that just identify an animal in a certain location? So in this case, we got data from these automatic feeding recording systems, and just we only use the data of which animal is at the feeder and for how long it stayed at the feeder, and then which one came next, and so on and so forth. And so this started a while ago with my collaborator at Michigan State, Janis Sigford, and a former student, Belsi Angarita. And the idea was that with these automatic feeding systems, the most common use is you sum over a period of time, over a testing period, all the visits from each animal to the feeder, for how long it was in there, and how much feed it consumed or it used or disappeared while the head was in there. And based on that, and then you measure initial weight and final weight, and do some clever data analysis, and you come up with a feed conversion ratio, residual feed intake, or other measure of feed efficiency. What we did here to take advantage of existing data from this type of sensors is analyze every single visit individually. And in addition to which pig was eating at that point in the feeder and how long it was eating, we look at who came after it, and if the pig that came after it came immediately after the eating pig left, or immediately after, or a long time after it. And then based on that, we started to track, are there any pigs that just by following another pig at the feeder are causing the front pig to have a meal that is shorter than the average meal of that animal. We know that animals that stay for longer at the feeder and shorter time, we know that there's that variation, has been extensively studied, but that's the animal that comes behind affect that. And so after that first work a while ago here at Iowa State, working with Andrea Nunez, and this is a collaboration with PIC. We analyze a large number of feeding records from like 4,500 pigs almost. After clean, etc., is what we left with. There were 277 groups of pigs analyzed. These interactions are within the group. And then we analyze it with a model that look at how long an animal was at the feeder depending on who followed it. That's called the social effects. And we had 2 types of social effects. A social effect that was due to the genetics, and the other one due to the permanent environment. This is a technical term that breeders and geneticists are very familiar with, but the idea is this. These 2 effects, the social effect of an animal, the genetic and the permanent environment, are intrinsic to each animal and follow the animal through the whole production system. They are kind of permanent, both of them. But one is due to the genetics of this animal, so it could be passed along. It could have been received from the sire and the dam, and could be passed along if this animal was an animal that would go into breeding. While the permanent environmental effect follows that animal for its whole life, or the production cycle, but is not inheritable. So when it comes to behavior, this is the difference between nature and nurture. The permanent environmental effects are things that are learned by the animal behaves that way their whole life, tends to behave that way, and the genetic social effects is the animal tends to behave that way because of its genetic effects. So one has implications for management maybe, the other one is clearly for breeding. And what we do, geneticists do, is they try to estimate this, what is called variance components. These are a way to estimate how important each of these factors is for the final phenotype, for the final trait that producers will observe. And of course, we compare different models. Is there or is there not a social effect? What we found, we went from a very complex model to a very simple model that didn't have any social effects. Models with social effects, with direct and social effects, explain more variation. So there is a component of the animal that is following in how long is the meal of the animal that is eating. And that is inheritable. But also, probably there is a permanent environmental component. These two are very hard to separate from each other. But there is a potential for both, for affecting feed intake and the way the animals cooperate in groups through selection, but also through management if we pay attention to this type of signals, analyzing the data in this way. So it's a moderate percentage of variance explained by the best model, but it's around 18%. So this is roughly 20% of the variation is explained by these two genetic components, which is actionable from the point of view of selection. And then, more recently, my other student, Juan, also using the same data set, she started to look at not just the effect of the following, but just who follow whom. And was this completely at random, or is there a preference for following? And this is also very important, because if you have an animal with a very strong social effect, negative effect for feeding, but that animal only follows one or two animals, it will affect the performance of one or two group mates. But if that animal, it tends to follow every animal, its social effect, it will multiply, it will affect many, many animals. So the numerical technique that she's using is something called a social network. This is a numerical method that is used a lot to analyze human interactions. It's been in use for a long time, and basically it's a way that you look at all the possible interactions and how many, let's say, the proportion that each pig follow each one, and then based on that come up with summary measures of how the social relations in this group work. And then you can get some network or group level measures like density. And so this is just how the group works. And what we observe is that over days after being put on feed, in this type of feeders, the density of the network increased and kind of snake around an average value. So the network was very, very sparse at the beginning and very dense, or much denser after a while. And this is to be expected, because at the beginning, as many of you know who have worked with this type of feeder, animals are learning, and then they don't go off as often, etc. Then when they figure it out, they start to go. But what is interesting is sometimes there's drops in that group. So now what we want to do next, and I don't have any data yet, any results to show you, but what we want to do next is if those sudden changes in the network dynamic at the group level are indicative, for instance, of a disease outbreak or maybe a heat stress event, etc. As you can imagine, those of you who have worked with a lot of data from pig operations, even from nucleus farms that collect a lot of data, sometimes it's hard to get this data and to align them. But this is more or less our idea. So the other one that I want to talk about is using computer vision. And today you saw some great examples from Matt Culberson from PIC and all the cool stuff that they are doing. This is an area that I've been also very interested on. And I started working with Thomas Norton from Leuven and Yannick Seaford from Michigan State a while ago. And now I'm collaborating with Santosh Pandey and with David Rosero from Iowa State as well. And I keep working with my previous collaborators to work on this. And one of the problems that we are working on is on animal identification. I won't talk much about that, but that's a problem. And then another problem is the scope of validity. And the scope of validity means if you have an application that runs, you collect data from a farm and it works very well, etc. If you go to the next farm or to the same farm next month, will it keep working, or you have to kind of retrain the whole machinery again? And then unfortunately, in a lot of the scientific publications, including our own, the scope of validity is very, very narrow. So I always try to keep that in mind. So one current project in computer vision is what is similar to what you saw today from Dr. Culberson, is to detect lameness. But we are trying to do this with pigs early in the pig's life. And the idea of this, it could have a use for phenotyping for breeding, but it's mostly for management. And the idea is that we have a set of experiments where we do recordings regularly, and these pigs are subject to different types of nutritional deficiency early in their life, and this is also a collaboration with our swine nutrition farm, and especially Dr. Gabler working there. And so we want to see if we can use, for instance, locomotion analysis to detect nutritional issues, mineral deficiencies or imbalances in early growth pigs. And what we want to do, because our end point is to do a system that is kind of fast to use in field conditions, farm conditions, we want to use simple camera devices. So instead of a high resolution, high frame rate camera, which is the ideal, we want to see how far we can get with, for instance, cell phone cameras, because as it was mentioned today, this is a tool that is very commonly carried by workers at the farms. And so today I will just show you data from a very small study, but what is interesting is these animals were followed over time, and they were subject to different phosphorus calcium ratios, more than levels, and then so we expect them to develop some locomotion problems over this time span. They were actively growing, especially for the most extreme treatments. And the way this is usually done is this is not showing very well. Let's see if I can do it again. So we come up with these key points, and then we record the animal and walking in front of the camera, unrestricted in this case, and then a computer starts to automatically place these key points on that animal. So now the animal is reduced to this wire model, and then we analyze the wire model, the angles, and how it walks, etc. And that's how we want to come up with a score. The first impulse is to use just to try to reproduce the human score, the human front leg score, back leg score, and locomotion score. And for that, it does the computer vision does a pretty lame job in our case. Today you saw one that was working great. Yet, what would you say if someone tells you that you have a system that reproduces a human locomotion score with 99% accuracy? What would you think about that? It sounds like great, but we know that the human is not 99% accurate, so it cannot reproduce that over and over again, right? So the maximum accuracy is the maximum accuracy, the maximum repeatability of a human scorer, which is around probably 85 or 90%. So we have room for improvement, but just doing that won't get to that place. And our long-term plan is to get just objective measures that get to what is important in the production system. For instance, performance at the end of the production cycle in the case of growing pigs, or for instance, stayability in the case of a sow. But because we are academicians and not engineers trying to do to crank out the technology, we are slower, but also we look into the details of this. And one thing that I ask my students, okay, what is the computer looking at? Because you put all these points, what is this looking at to make the decisions of what is a score higher or lower, or this or that? And in general, it's looking at the right places. The most important one usually is the back angle. So the back angle of the animals as they walk in many quadruped species is a good indication of how good or bad they are walking. So that's one. The other one is that depending on the type of locomotion score is to put in a little bit more weight on the back or a little bit more weight on the front. So it's kind of looking, without telling, it's looking at the same places that the trained human scorer is looking at. It's just not doing it in the same way, and it's not getting to the same endpoint as revealed by this limited accuracy. So this is an area where we want to keep working, and we want to do these AI systems that are semi-mechanistic, that are informed by the human observer as well, and they look more at where they should be looking, as opposed to overwhelming this with data and just letting the data speak for themselves, which in our experience works in the short term, but in the long term has little generalization to other scenarios. And the final one that I want to share today is about animal tracking. And this is another obsession of mine. I want to track animals all the time and identify them. And we started working on this a long time ago, and we did a lot of reviews, we tested a lot of programs, etc. And you know, it works until it doesn't work anymore. And that's the long and short of this. So more recently, with our postdoc, Yebi, we started to work using fundamental vision models. And these are models that are trained with millions and millions of videos and images from Meta. So whenever you put stuff in the internet, in Facebook, or in Instagram, or even share videos in WhatsApp, apparently these guys are using those videos to do fundamental image analysis. And based on that, then they train models. It's pretty clever the way they do it, and they put these models out for the public to use. And it's mostly trained on human movement, some quadruped movement, and interaction between humans and animals, especially humans and dogs. It has millions of images for that, very few images for and videos for pigs. So if you want to help, just upload your pig videos to Facebook, or depending on your age, I use Facebook. So we put it to work automatically, and then you need like a very clever young trainee who come up with an analysis, does all these analysis of weaknesses, etc. And we add a little bit of touches. Modifying the whole thing is extremely complex and beyond our goal, but you can touch up in some places and improve the performance. So. And then you need undergraduate and other collaborators willing to look at the videos and tell you this is wrong, this is right, etc., and keep improving. And so this is what we are working on right now. And basically, we analyzed thousands and thousands of video clips, 1 minute to 5 minutes, and with 10 pigs in a nursery. We have lots of these through collaboration with David Rosero. And we narrow it down to 4 different types of errors. But the most important one is here, when there's a bunch of pigs together, it's recognized just as a single pig. It's not that clever yet, the algorithm. Another one that is very critical is when there is this switching of identities. So there were 2 pigs here, like doing stuff together, and when they come out, the pig that was marked as pig 1 now it switches to this pig. This is very bad. This is very negative for the tracking error, because from that moment on, you lose completely the identity of the animal. And also this accumulates over time. So if you have a 1% error rate of this every minute, every 10 minutes, this will be a huge error. Almost no one will be correctly identified. And so through the analysis of this, and what we found is that when the pigs were stacked, there was higher error rate, but then the correct track was very low over a whole day when you had error switchings. So due to this, you couldn't do it. But after doing some adjustment, now we get to almost 95% accuracy for tracking pigs, as long as the pigs don't pile up. As soon as they start to pile up, then we lose the identity of the pig. So, but what is interesting now is that we have this video. This is the original video, and this is one of the outputs. As you can see, if you look at this image has much less data than this, but still you can figure out what a lot of these pigs are doing by just looking at that, right? You could, if there are 2 pigs fighting, you will be able to tell. 2 pigs competing for feed, you are able to tell if you have a keen eye for this. So the idea is replace these images with these images and do the processing on farm, and then transmit this to a brain that will do the analysis of the behavior. And then on top of that, we have these tracks. So with these tracks, we can extract a lot of phenotypes from them. And one very commonly used one, and it was mentioned today by Matt Culberson, is how long the animal was active during the day. There's animals that are more active, animals that are less active. But also, by looking at the pattern of movement, you can also figure out, for instance, aggression or fighting or other type of interactions. So this is what we are working on right now. To go from these images to this is we are pretty confident in this process as long as the animals are moving. We are also working on the ID of the animals. As you can see here, it's pretty simple because we write a number, we scratch a number on the back, but we are now brainstorming about a more sustainable solution than this. But then now our focus is, once you have this type of data, which are very simple, what can we learn from this without having to watch a video? This video has too many errors and too many distractions to a computer. These two videos, quote-unquote videos, are very clean, are simplistic but very clean, so they have more chances of producing a usable signal that is widely replicable. So, from this, we expect to have like total animal activity, drinking, eating for specific activities. Proximity to other animals, this is a big one, and not only proximity but also orientation. So if the head was close to the rear end head of one sow close to the rear end of another sow or gilts all the time, and then the one that was in the front shows up with a tail bite, then you can start to infer who caused it or who has a chance to have caused it versus the one that were nowhere close, and so on. And so we want to go from proximity to actual specific interactions. The level of complexity increases as we go. I order those on purpose in that way. But as we produce this, and these are pretty low-hanging fruit, we can do, for instance, for management, early detection of disease or prevent, control thermal stress, etc., because you see drops in activity or specific activities or general activity. But also, as we get to the more specific phenotypes, we can select less aggressive animals, or either of these could be used to select more resilient animals. And today you will hear a lot about resilient from my colleague Jack Deckers in a completely different context. So, oops, did I mess it up? Yeah, so is this supposed to move? No, maybe not. To conclude, we are working actively on phenotyping animals in groups. Sometimes that implies phenotyping freely moving animals, let's say using a phone or just using a camera to watch all the animals at the same time. And with that, we want to study like individual animal locomotion or activity. Yeah, it was supposed to have something here, but it's not showing up. Well, it doesn't matter. And I'm very interested in the interactions between animals. So based on their activity or based on their visits to a feeder or use of, let's say, a drinker with an RFID, etc., what are the animals doing together or away from each other? And then use that to select animals that are better adapted to this production context. For instance, they stay for longer time, or they are less aggressive, or they recover faster from negative stimuli. But we are also interested in management, using this for management decisions, because these systems could be deployed in the real time. So, for instance, detect nutritional deficiencies or welfare and health issues. And that's all I have for today. Thank you.
Okay, are there any questions for JP?
Thank you. So obviously there's a lot of things that can be applied of what you talked about in nucleus herds. Mm-hmm. What do you think is the most direct applicability? Which technology, when it comes to producer herds, which technology and application do you expect to see first?
For instance, for growth finishing, the one that I expect to see the most is one that didn't show. is cameras for estimating weights with a specific purpose of planning closeouts. I think that for that, there is an enormous potential for making money, because a lot of money is left on the table due to shipping out pigs in different states or having like a leftover, and these if the cameras can estimate weights accurately on a daily basis, you can plan. And then my sales pitch for my work is, if on top of that you throw some social effects models, so you can estimate, if I remove so many pigs, the growth curve of the rest will change, and so you can put that in an optimization program, an intelligent system that will help you plan closeouts. I think that's the one that a lot of the large integrators are expecting to see it work. Then another one that we are working on, we're starting to work on with Isaac, but I don't have any results yet to show, or any even process data, in farrowing, is a camera systems to monitor farrowing and to send intervention alarms for animals that need to be sleeved, etc. I think that's another one that is coming up. A lot of groups are working on that. I think those are the two most promising I see, but for making a difference. Mm-hmm. Yeah.
Great stuff, Juan. My question for you, kind of along the lines of what Jack mentioned. Do you think on that tracking model that you mentioned, I know that you had some issues on the overlapping part, but if we want to, for example, follow pigs that are not eating in the sow farm, that might be easy today with those electronic feeders, but for growing pigs, if you have a camera, even though you have the overlapping thing, but you would expect that the pigs that are sick in a pen, they wouldn't be moving. So for that tracking system, they would be, let's say, hold there. So do you think like targeting those pigs with that tracking system could have helped you where they identify those pigs?
So you are onto something, Edison. Actually, our long-term goal for that, and the collaboration with David Rosero and my group for that, is because this is done in the Iowa State swine nutrition farm, we have also data on each of those pigs. This is early nursery. This is the first 3 days or 5 days in the nursery. And so we have data on animals that had to be pulled due to low performance or stuff like that. So we want to find from this movement and activity, etc., early indicators of that, so it doesn't have to be like in a very extreme condition for a caretaker to realize and pull them to the hospital pen, or just to remove the pig. However, I'm not sure that this will be implemented as such in a commercial farm. Maybe it's a research tool from which we can emit some other recommendations, and probably for that type of pig, the quote-unquote most promising could be a monitoring of the feeder itself and trying to figure out that a pig is being missing in that for a full day or 2 days in that pen. That's how I see it after knowing the difficulties. But yeah, we're planning on using that for that purpose, but in a research setting, not thinking of delivering anything for commercial.
Let's thank our speaker.
Thank you.